Um, all right, so yeah, welcome back to this weekly book club meeting. Um, I didn't really prepare any slides this week, but I do want to make a couple announcements, regarding next quarter, just so that we're all aware. So a couple books so that are in the works for next quarter. So we've got um, this Signals and Systems book, right? And this is on O'Reilly, I think. Yeah, it's on O'Reilly. So this is like good for EE 228 and 328 as it's taught at Cal Poly. And so this is um, typically a pretty involved subject that depends a lot on differential equations and a good, strong understanding of trigonometry, really, at the end of the day. But I think it's approachable, at least after going through a first circuit theory class as we are doing right now. And so we'll try to cover it next quarter, if there's sufficient interest, obviously. And again, this is like second or third year material, so there's a lot of mathematics involved, but I think we can kind of easily get around the math and kind of get high level topics out of it at the very least. And the thing that I like about this is that it also includes a lot of MATLAB. Um, And so presumably you guys have seen a lot of the MathWorks little certification things. Those are very high level and it's hard to actually get practical experience with those, but I think this book does a good job of actually giving more practical knowledge in MATLAB. So we'll take a look at that and see how it goes. Matthew Sadiku is a really good author. He's a professor emeritus, I think it somewhere in Texas, I believe. But he's also co-authored a book with Professor Agbo on communication systems. So Professor Agbo unfortunately passed away, I think last year. Um, but he was a great professor. He actually worked at Bell Labs, I believe. So very, very strong person in the communication field. Um, but anyways, right. So this is kind of a next book potentially for next quarter. Um, and then another book is this book by Christopher Sue. I'm actually not familiar with Christopher Sue, but he's based out of Canada, I believe, but he seems to have a good book on electronic devices that's available to all of us. And this is through Springer. So this is a different kind of like database for that we have access to. There's a lot of good books on here as well. But again, that's by Christopher Sue. I don't think I had it bookmarked anywhere, so I'll just try to pull it up here. Yeah, so it's this guy here. Um, and so this will cover what's typically taught in EE 306. So that's your semiconductor theory class, and it's kind of just an introduction to the mathematics behind a lot of semiconductor devices like diodes, BJTs, MOSFETs, primarily. So I think this is I flipped through some of the pages, right? It was kind of challenging to find a good book that we all have access to that, free on with our license. So I think this one did a fair job. So I might try to read through it first and then we'll see if we continue to pursue it next quarter as well. Um, but yeah, so unless there are any questions, we can proceed with the material for this week. And again, I don't have slides prepared, but figured we could just talk through some things. And so let me share my iPad screen here. I guess just out of curiosity, has anyone taken differential equations yet? Or are we still in the calculus series. No differential equations. All right. Well, we'll try our best here. All right. So today we're looking at chapter 7. It's a little too thick for me here. So chapter 7, and this is on first and second order circuits. Um, and if you're wondering why we're kind of doing this with the iPad today, it's one, because I'm a little bit lazy, and two, there's a lot of math involved, and I didn't, it might make more sense just to write these things out, because it's more it's a little bit easier to follow, I think, written out. So we'll jump with the learning goals. So first learning goal, I think I'll just stick with the this guy here. So we want to calculate initial values for inductor currents and capacitor voltages in transient circuits. And I'll post these notes for those of you that are trying to follow along here. So inductor currents and capacitor voltages. So as a reminder, last week we kind of looked at, what those kind of defining equations are, for, the voltage and current for inductors and capacitors. But just kind of as a recap, um, we had the voltage for an inductor is L di dt, and then the current for a capacitor is C dV by dt, right? And so whenever we have circuits that involve these first order derivatives, we actually need some kind of initial condition to fully solve the circuit. And so that's kind of where this whole idea of calculating the initial values comes from in the first place. Um, and then our second learning goal here is to calculate voltages and currents in first order transient circuits. And for those of you that are unfamiliar with this definition of order, right? The order of a circuit, or order of a differential equation, right? A system of equations, really. This is just referring to the highest order derivative that's present in the system there. Um, and we'll kind of get to that into more detail. But I just wanted to make that statement because I understand that not everyone here has had a course in differential equations, but I hope we all at least know what a derivative is. And then lastly, we want to calculate voltages and currents in second order transient circuits. Right, and so you'll notice that the learning goals for this chapter are very brief, but this is actually getting into a very, very difficult territory, at least from what I'd gather after reading this chapter here. Um, and so this is the type of analysis that I don't actually do every day. And most people, at least that I'm aware of, don't actually do this type of analysis. But again, it's kind of important just to be aware of everything that's going on here. All right. So those are our learning goals for this chapter. Um, so then moving along here, right? So the first thing we're kind of looking at initial initial values, but I think we'll come back to that after kind of at least introducing the idea of these first order transient circuits. So they kind of open with this example. So we're going to consider the following circuit. So we have a voltage source, and then it's driving a resistor, and then there's a capacitor that's kind of being switched right there. So there's our capacitor, and then got a switch that is normally in this position, and then at some amount of time later, we move it over there. So here's our capacitor, here's our voltage across capacitor. This is just some resistance of the source, and then this is a voltage source. So this is kind of like a good way to just kind of remember what's going on with these energy storage elements really is what I think this example is trying to get at. So basically what's going to happen, right, is this circuit will be in this state for some amount of time, right, where it's just the resistor, the resistance of the source, the voltage source, and this capacitor. Um, right, and we kind of had learned a little bit about the behavior of a capacitor and how it's related, its current, right, is as a function of time is given by the capacitance times this change in voltage over time, right? And so if we kind of assume that the capacitor is initially uncharged, um, right, such that the initial voltage is zero, then over time, right, the current is going to start to decay, right? Because the charges are going to start building up on that plate of the capacitor. And then as it charges up, the voltage across this resistor, which is really the only current that we can um, determine right away, right? So the voltage across this resistor is going to start approaching zero, right? So as that capacitor voltage goes up, it's at some point it's going to go up to the point where it reaches the voltage of the source, right? And then at that point, the voltage across the resistor here is going to be zero. And so let's just draw that out. So over time, the capacitor voltage, well, so it's going to start off at zero because we're assuming that it's initially uncharged and it'll build up, up until it reaches the voltage of the source, right? And so once that voltage is equal to the voltage of the source, and we look at the voltage across this resistor here, maybe, right? So that's going to also, well, so it's not going to go up, right? It's going to actually start at Vs because this is initially zero. So this is voltage across the resistor, this is voltage across the capacitor. So it's going to start at Vs, and it's going to actually decay downwards to zero. And so when that happens, the current is also, since the current is given by the voltage divided by the resistance, and the voltage goes to zero, then our current is also going to zero. All right. So that's kind of like a recap of kind of what happens, um, for this kind of capacitor charging circuit, really. And the next thing that we're kind of interested in is what happens when all of a sudden the circuit switches to this configuration where we just have the capacitor and the resistor, right? And that's kind of what happens when the switch moves over to the other position. And so assuming that this capacitor, you know, at the moment that it switches position there, is fully charged, right? It sees the voltage of that source, as we had just talked about. Well, it's going to discharge the energy, the stored energy in here through that resistor, right? Um, and so they've given out the, little differential equation that describes this circuit. And so this is actually what's kind of called a natural response. And we'll get into what all that means in a bit here. Um, but basically, if we were to do KCL, right, if we call this ground and we just do KCL up at this node, right, if we're looking at VC here, because that's VC, well, we have two currents. The first current is given by the capacitor current equation, right, which we had up here, C dV by dt. And just to be consistent, I'll call that VC. And then we have another current, right? So again, I'm doing KCL at this node here at the top. So we have another current leaving. So if I'll just add that. Um, and so that's given by VC over R because the voltage across that resistor is also VC. These guys are connected in parallel, right? And so I got two currents leaving, none going in. So I'm just going to sum those equals 0. Right. And so as you can see here, this is a first order differential equation in VC, right? Because we have a first derivative here and we just have another term there. And so what we usually do is we kind of remove the coefficient from the highest order derivative. And so if you move that around, right, if I just divide everything by C, then I'm given this equation here. Um, and so we'll see, if you actually go through and study differential equations, and we'll talk about it here real quickly, actually. So again, we have this equation, right? So dVC by dt plus 1 over RC VC is equal to 0. All right, so that's our differential equation. Um, and it takes the form, this first order form. So I'm going to draw this out. So this is the first order differential equation form. And this is a very general form that I'm writing here. So I'm just going to call my variable x, just some arbitrary variable. It can be anything really. So I take the first derivative of x, and then I add a times x of t, and that's just equal to some function f of t. Right, and this is the general form of a first order differential equation. Um, and so you can see it's first order in x. We say it's first order in x because the variable that's being differentiated is x, and it has a, which is just some constant, and then f is called a forcing function. I guess f of t technically is called a forcing function. Now, what you'll notice in our equation here, our forcing function is 0. And so that actually has a very special name, right? So this is what's called really an unforced equation. You'll also see it called the homogeneous. This is the homogeneous equation because all of the terms are adding to, are combining together and equaling 0. Right? So it's called the homogeneous, it's called the unforced, it's got a lot of different names. But in the general case, when we have a forcing function, right, this is called the forced response, really. And if you study differential equations, you'll see that whenever you have something like this, right, of this first order differential equation form, the solution to this differential equation has two parts. The first part is, I'm gonna write this. So the solution to the first order differential equation has two parts. And so just to be clear, the solution to a differential equation is a function itself, right? And so this is kind of a tricky nuance, right? We're no longer looking at real, just numeric solutions. Our solution to this is going to be a function. Um, and so this solution has two parts. So x of t, right? There's the first part, which is called the particular integral solution, or just the particular solution, I've seen it called as well. And then it has this part called the complementary solution. Okay. The particular solution, so this is the particular solution, and this is the complementary solution. So the particular solution, so if x of t equals xp of t solves, and so I'm going to keep the naming, the numbering convention of these equations. So this is 7.1, this general form. So if x of t is equal to the particular solution, xp of t solves that equation, um, and x of t equals xc of t solves the homogeneous, right? And so the homogeneous is actually just the same equation, but instead of a forcing function, we're actually just considering, right, setting it equal to zero here, really, right? So this is the homogeneous equation. Then x of t, which is the sum of these, solves the original equation completely, right? And so this is an important theorem of differential equations, and you'll kind of dig into the nitty-gritty once you get to that class. But for now, you'll just have to kind of accept this idea that in order to um, get a solution for this first order differential equation, you'll need two parts to the full solution, right? You find the particular solution for a specific forcing function, and then you find the complementary solution that solves the homogeneous equation, and then you add those together, and then it fully solves the differential equation. Um, right, and for this, um, so one known solution for this form here. So a known solution to this first order form is x of t is given by k1 plus k2 e to the minus t by tau. Um, and if you have studied the capacitor, charging and discharging equation, this will look somewhat familiar. But we can break this down into a steady state solution. Let me make sure that they called it that. Yeah, so the steady state solution. And so this idea of steady state comes up a lot in electrical engineering. So If you're comfortable with it, that's good, but if not, you'll get there. And then this, um, well, this is just another part that decays to zero, right? So I don't know if they called it anything here. I want to call it transient. Let's see if they called it anything. I don't think they called it a transient. Um, but as you can see here, as time goes to infinity, this term dies out, right? Because you have e to the minus t as a factor, being multiplied by this K2 term. And so as time goes on, this exponential term goes to zero. So the whole term effectively goes to zero as time goes on. Um, all right. So typically when we're looking at first order differential equations, um, we're going to just assume a solution of this form, especially, in the unforced case. But let's kind of take a look at maybe what that looks like here. Um, right. And if we were to go back up to this, then, they've written out here that the solution takes this form. So V naught e to the minus t by RC. Um, and looking back at this form here, you can see that in the unforced case, we actually don't have a steady state solution. We only have this term that's going down to zero, which makes sense because in this circuit here, right, the only thing that's happening is the capacitor is sending out energy, and that energy is being dissipated through the resistor, right? There's nothing that's really forcing this circuit um, to have any kind of energy. Um, Whereas in this first circuit here, right, we have a some kind of voltage source which is supplying energy, right, and power to the circuit. Here, the capacitor is just discharging, so it makes sense that we don't have a steady state term here. We only have the transient part, which is just decaying down to zero. So that's kind of nice how, these differential equations come into play and how it really does help you visualize what's going on in the circuit once you kind of understand kind of like the differential equation part, I guess. So that's kind of like the hard part, really. All right. So kind of with that, probably be good to jump through a quick example here, unless there are any questions, right? So all we've done really so far is go over the first order form and then kind of recall, these initial um, capacitor and inductor equations that we looked at last week. So not too much so far. Um, all right. But yeah, feel free to stop me at any time if you guys are feeling stuck here, because I know it's kind of a lot to take in at 8 p.m. All right. So in this example, we're looking at circuit here, and it's got a resistor and then a capacitor in parallel with another resistor. All right, and this has a switch here, and we're going from position 1 to position 2 at time 0. And we're kind of just assuming that the capacitor has fully charged. Um, and it looks like they don't have the C there. Oops. So we've got a capacitor and 6 kilo ohm resistor and a 12-volt source. Right, and so the first thing that we kind of want to do here is determine the initial value for the capacitor voltage. Um, and so they've done that here. And an easy way to visualize that is just to look at what's going on. And so you'll remember that the capacitor, after it's fully charged, is an open, right? Because no more current is flowing through it. And so if we try to figure out what this voltage V of t is at time zero, we'll see that this is just a simple voltage divider, right? So if I do V of zero minus, right? So before the switch is thrown, well, my voltage is going to be given by 12, and we're looking at the voltage across this 3 kilo ohm resistor, and the total resistance, right? Let me just draw this in. So 3K, 6K, 12. Um, so I've got 3 in series with my 6, right? And if I know how to do math here, that's 12 times 3 by 9, right? So this becomes a third. This becomes 4 volts. And so 4 volts is appearing across the capacitor right before the switch is thrown, right? So we got 4 volts there. And then the next thing that we want to do is do just a KCL equation um, to figure out, what's going to happen to that voltage, right, when the switch changes. So when the switch changes, we're actually looking at this circuit. The voltage source is no longer going to be in the circuit, right, because I've thrown the switch and now I have this network where the voltage source has no path for current to flow anymore. I got my 6K, I've got my 3K, and I've got my 100 microfarad capacitor. And the voltage here is initially 4 volts. Um, but anyway, so we're going to do a KCL right at this kind of interesting node that's at 4 volts because this, we'll just call that ground. So if I do a KCL there, well, I've got, you know, 4 over 6 going that way. I've got C dV by dt, right? So C dV by dt. Um, and actually, instead of 4, I'm just going to do V. And then I've got another V divided by 3 going there. And that's going to be equal to 0. All right. And so you'll notice here that if I move some things around, right, if I first divide everything, sorry, so this C is going to be 100 microfarads. I'm just going to put 100 mic, and these are 6 and 3K, I guess. So if I move some things around, right, for example, so I want to get it into the form where I no longer have a term in front of my highest order derivative. So I'm going to divide everything by 100 microfarad. So I'm left with just dV by dt. And then if I look at what happens to these guys, right? So I've got 1 over 6K plus 1 over 3K, and then I can multiply this, or divide rather, by 100 mic. And so that's going to be times V, and this is going to be equal to 0, right? So this is now my differential equation effectively. And it looks like if you actually go through and solve whatever that is, that ends up just being 5. Right, so here's my differential equation, and this is just a homogeneous equation, so we can assume a solution of this form. So V of t is equal to K2 times e to the minus t by tau, right? Um, and kind of just to give you some intuition on why we assume a solution of this form, right? If you recall, the exponential function has a derivative, that has the same exponential function, right? So if I take well, actually, we'll just go and do this, right? Um, so if I take the derivative of this, I have k2, right? And then I'm multiplying by this minus 1 by tau term here, right? And I keep the e divided by e to the minus t by tau, right? Again, and this is just the derivative of v. And so if I take that k2 times minus 1 by tau, e to the minus t by tau plus 5v. So my v now, right, is k2 e to the minus t by tau is equal to 0. And, right, so if we go through and solve this, we can do so, right? We're trying to figure out what k2 is at the end of the day. I've got these e to the minus t by tau terms, which I can just kind of get rid of, right? I'll toss it over to the other side. So I'm left with k2 times minus 1 by tau plus 5 is equal to 0, right? And that's kind of assuming that e to the minus t by tau is non-zero, so we can actually divide it over. Um, and from here, we can actually figure out what tau is. Um, right, so we'll assume that k2 is non-zero, because otherwise it would be a very boring function if it was just 0, right? V of t is 0. That's not very interesting. So we'll assume k2 is 0. And so we'll solve for tau. So 1 by tau minus 1 by tau plus 5 is equal to 0. So tau, right, is just going to be a fifth, which is zero point 0.2 seconds. So if you'll remember, we talked a lot about time constants in EE 151. And so this is kind of the whole idea of a time constant, and it kind of just describes the rate of decay for a system, right? Especially first order systems where you really do have something that's literally decaying exponentially. And typically, if you actually have some kind of forced behavior, you'll also have, a term that is steady state, and you'll have the transient part, which is decaying. And so this idea of having parts of your system that decay over time, right, these transient behaviors, ends up being a really important idea for communication systems and control systems and pretty much the whole onslaught of curriculum that follows circuit theory. So, it's really important to keep in mind what these differential equations are, describing and kind of where this is all coming from. Um, so we've got this time constant, and we can then determine, right, that our so we had this, right? We had v of t is equal to k2 e to the minus t by tau, and right, we had assumed a solution of that form, and we figured out that tau is zero point 0.2 seconds by plugging this into the homogeneous solution. And again, this is the homogeneous. This just describes um, how fast the system is decaying. Let me make sure I copy it over correctly here. What we had, dv plus 5v equals 0. But we had figured out that tau is given by zero point 0.2 seconds. Um, And the last thing that we need to do really to solve this first order differential equation is figure out what K2 is, or I guess to properly write that in the form of a question, what is K2? And so this, to do so, we need to use the initial conditions. So if you recall, we had this initial condition that we solved earlier, that this is 4 volts across that capacitor. So our initial voltage is 4 volts. So if we use that, um, then our solution is actually just this, right? Because our voltage across that capacitor, the second that the voltage source is removed, it starts at 4 volts and then it starts decaying exponentially at a rate of zero point 0.2, seconds, right? Um, sorry, not at a rate of zero point 0.2 seconds, but with the time constant of zero point 0.2 seconds. And that's all there is to it. So we've got our voltage. We can actually also find out the current through any given resistor here, right? For example, if I want to figure out the current through R2, that's going to be V divided by R2, which in this case is 4, divided by 3. I want to say that's 3 kiloohms, right? So I'm looking here, 3 kiloohms. I'm just going to write milliamps, e to the minus t by 0.2 milliamps, right? So there's our current, there's our voltage. You could find out the current through the other resistance if you so please. But if you were actually going to go and simulate the circuit and kind of understand the transient behavior of it, it would look like this, right? And so if I were to maybe sketch this, if I looked at the voltage over time, I'd start at 4, and then it would just decay down. And actually, after 5 time constants, it's within 1% of zero, less than 1% of zero, right? And you can read about how that works if you want. But if there aren't any other questions, we'll kind of move on here. I know it's a lot to take in, I think. Kind of hard to I think it's getting progressively harder to cover this material in the amount of time that I had allotted. Um, this is very challenging stuff, but I commend you guys if you're actually understanding this because that's pretty good. Is there any questions on anything here? Um, Time constant, differential equations?
I
Nope.
have a question real
Yeah, what's
quick.
up?
So did we just use, so the purpose of like the homogeneous solution was to solve for tau, and then
Yeah,
we like plug that back into the form, like the V of t equals K2 e to the negative t over tau.
right. So, I mean, we're using the homogeneous actually mostly just because the system itself um, is effectively homogeneous, right? It's just decaying to zero, right? If we
Uh-huh.
if we did have something forcing the capacitor, right? If we actually had the voltage source um, switched on all of a sudden, we would actually need to use both the homogeneous and kind of like the particular solution. And so there are some examples of that in the book, but I kind of just wanted to start with this one because it's a little bit easier to digest, I think.
Okay.
Um, but yeah, going back to your question, yeah, you assume a solution of that form, mostly so that you can first figure out the time constant. That is correct.
Got it.
Yeah.
All right. Thanks.
All right. Um, So that's first order. Um, let's move on to second order, right? Because I think we get the general idea. Really the only difference with having a forcing function is that um, you would have to solve two of these differential equations and um, go from there. And there are good examples of kind of how to do that. And actually, maybe I'll take it to the group. Do we want to go over a forced example or move on to second order? Let's see if I can find a good one. Um, I think we'll just move on to second order, I think, unless there are any strong opinions otherwise. So, right, we had looked at a pretty simple case where there's just one capacitor, and generally speaking, when there's only one storage element, you'll have a first order system. When you have more, you'll have however many derivatives, right? The highest order derivative that you have in your system effectively. Um, so I think maybe a good example, since we already did like voltage sources, we'll do voltage source again. All right, so second order systems, again, will have two energy storage elements, typically at least. So there's a capacitor here, and now we've got an inductor there. And this is R, this is C, this is L. We're kind of interested in the initial voltage across the capacitor and the initial current. Well, I guess in this case, we're just looking at this is I, right? We've only got the one loop current really, so, and then they've got this as Vs of t. All right, so if we do a KVL around this loop, I've got my voltage source, which again, if you think about it in terms of differential equations, this is a forcing function, right? I've got the voltage drop across this resistor, which is R times I. And just to be clear of the polarities here, I'll just write all these like so. And again, if we imagine traversing this loop, if I'm coming out of VS, I'm going out of the higher potential. So I'm going to, this is effectively one side of the equation. All of the other terms are coming out of the negative, right? The lower potential. So I'm just going to throw it onto the other side of the equal sign there, right? Equivalently, you could do VS minus, minus all these terms, but we'll just stick with this. Um, so the next thing we have is the voltage drop across the capacitor. And we know that the current in a capacitor is given by I C dV by dt. So if I solve for the voltage here just by means of, you know, moving over the differentials, and I know I'm skipping a bunch of steps, but the idea is, you're going to move the dt over, you'll take the integral on both sides, and you're left with v is given by the integral of I times 1 over c, basically. And so they've written it like this. So they've got from some initial time t to final time, or initial time t naught to final time t, I of x dx plus the initial capacitor voltage, right? And this kind of plays on the idea of adding a constant, right? When you have when you're taking an integral, you're always taught, to add some kind of constant. And so this is kind of interesting, right? This constant, in our case, comes from the initial condition of the capacitor voltage. Um, and that's, generally the case where that constant C comes from, right? Is the initial condition of your system. Um, but anyways, so then the voltage across that inductor is given by L di by dt. And so now we have something that looks like a differential equation, but it's not quite there yet. And so what they do here is we're going to actually take the derivative of everything so that we can get rid of that integral, right? And in doing so, I end up with d vs by dt. Um, Let me just make sure. Yeah. So d vs by dt is equal to r di by dt plus 1 over c I plus I want to say that that goes to zero, the VC term. Yeah, so that goes to zero. This is a constant. So that goes to zero. And then we have L di, sorry, d squared I dt squared, right? So the second derivative of I there. All right. And here we have a second order differential equation form. Um, so how do we how do we solve this? Without any knowledge of differential equations, how on earth are we going to solve this? And actually, it's a very similar process. So we're going to start off by looking at the general second order form. Right, and so this takes the form d squared x of t, right? So this is a second order differential equation in x or of x, however you want to say it. We have a constant on the first order term, and we have a second constant on the zeroth order term. And this is all going to be driven by some forcing function, f of t, again. And so what follows, right? Again, so if we have x of t is given by xp of t, and I'm going to call this equation 7.12 as they've done in the text. So if this solves 7.12, right, this is called this particular solution again, and x of t equals xc of t solves the homogeneous. All right, and that again, that's just this equation where the forcing function is zero, right? It's unforced, nothing's happening. So if we have these two, if we have the particular solution and we have the complementary solution, then by, some theorem in differential equation land, we have the sum of these two fully solves the original second order form. Um, and I think it might be a little confusing, right? Because, well, hey, if we found our particular solution that solves this guy, why do we even need the complementary solution? And I had wondered about this as well. And it's a little bit more apparent in this case, right? We have a second order system, right? So we need at least two initial conditions to solve this thing, right? In the past, we had only needed the one initial condition, um, but here we certainly need two, and so we certainly kind of need these two equations to, be able to get two solutions, right? Two unknowns, two equations. We can kind of solve the system. Um, I'm kind of not completely sure why you need both in the first order case, right? And that kind of just probably my lack of differential equation knowledge. But in any case, right, by this theorem, you need the particular and the complementary to solve the second order form completely. Um, all right, so it's 10:03, or I guess 9:03 for you guys. Right, so we'll try to push through this a little bit more. It's 7 more minutes at least if you guys are still down here. Um, all right, so what do we do now? We have the second order form. We know that we need a complementary and a particular solution, but how do we get there? And so much like in the first case, we kind of just exploit the fact that there's a known form of the solution and we run with it. And in this case, we kind of assume that much like this first case where we're looking at the exponential function, right? We really like the exponential function because its derivative has the same exponential term. And so that makes solving the homogeneous equation really easy, right? Because like we had done over here, maybe not there, over here, we can just get rid of that exponential term and kind of add up the parts and then set it equal to zero. So we're going to run with the same idea that we kind of assume something that has an exponential term in it. Here they say we assume that x of t is given by k e to the st. Um, and if we assume something of that form, right, then again, it makes this differential nonsense going on here a little bit more digestible, especially for the homogeneous case. Um, so without going through all of the math, it actually turns out that, you know, if we run through a bunch of stuff, right, if I were to go through and I plug this ke to the st into this second order form, then I get something that looks like this. I have s squared um, plus 2 zeta omega naught s plus omega naught squared. And so where this is all coming from um, is actually they took down a bit. They took A1 to be 2 times zeta omega naught and A2 to be omega naught squared. Um, and this actually makes analysis simpler later on. And so if you do that, right, and you kind of plug this guy back into here, what ends up happening is all the exponential terms end up canceling out, right? And we're kind of just left with an s squared coming from the second derivative, right? If I take the second derivative of x, I get an s squared term out. And then I get rid of these k terms, right? Because I can just move them over, divide them over to the zero side, right? And so I end up with this equation. Um, and so this is called the characteristic equation. And this is a very, very important um, equation that comes up in almost every single class, following circuit theory, at least in the world of electronics. And you can glean a lot of information from the characteristic equation. But first, we'll just talk about the roots of it, right? So the roots of this characteristic equation um, are actually pretty simple, right? You can certainly get this. And this is just a quadratic equation in S, right? So we have our first, or actually, if I were to just write it out, the whole quadratic equation. So my negative, my negative B effectively is this 2 zeta omega naught, plus or minus square root. My B squared is going to be 4 zeta squared minus omega naught squared. 4 AC is going to be 4 times omega naught squared and all over 2, right? And so I got this plus or minus, which means I have two solutions. My zeta omega naught plus omega naught zeta squared minus 1 going to be my first solution. My second solution is going to be minus zeta omega naught minus omega naught square root zeta squared minus 1. Right. And so you can quickly see why I chose not to really put together slides for this. It's a lot of math. Um, so these are my two solutions to write the characteristic equation, which describes the homogeneous solution to the second order differential equation. Right. It's a lot of stuff going on here. Um, but what you really need to know, and if you take nothing else away from this, is that there are three cases for this. Right. The first case is when zeta is greater than 1. This is called the overdamped case. And if we look back at, this, our two solutions, when zeta is greater than 1, this is real, right? Both of these. Both of these are real. Um, and so I'm just going to talk about this. I'm not going to write all this stuff down. You can read about it a little bit. So when this term is real, right, it's kind of just a decaying exponential, this whole second order solution. When we have zeta less than 1, right? So if zeta is less than 1, I'll write that. So case 2, zeta is less than 1. This is called underdamped. And this is a big problem in a lot of systems. Um, and what happens here is because zeta is less than 1, this whole term under the square root is complex, right? You have zeta less than 1. Oh my God. If zeta is less than 1, then zeta squared is surely less than 1. And this whole thing becomes negative. And when that becomes negative, then we have some kind of complex behavior. And so that takes the form of some kind of sinusoidal function, right? So what happens in the underdamped case is usually, right, have some kind of oscillatory response, right? It's usually decaying at least, right? So that's the underdamped case. Our overdamped is kind of just dying out, right? So it just dies out. And then case 3, when zeta is equal to 1, this is just called critically damped. It's on the border of being underdamped or overdamped, and it's basically just the fastest, um, not the fastest, kind of like the longest amount of time to decay before, becoming having some kind of oscillatory behavior. So it's good to talk about these ideas, right? just so that you're aware of where they all come from because they come up over and over again. Um, and I guess that kind of concludes my little spiel here. Unless there are any questions, I'll stop the recording here. Um, we definitely did not get to chapter nine, but or chapter eight, but we're making progress. That's the more important part, I think. So next week we'll talk about chapter eight, and so that's AC steady state. Um, that's a little bit easier to digest, right? A lot, like I said, like you don't usually do differential equations in practice, but good to be aware.